All right, it's recording. So this is technically exercise, I think it's 9F, potentially in the older textbook, or 9E in the new one. It's standard deviation is what the topic is about. So two things I want you to take away from today. One is what is standard deviation? And two, how to use normal distribution or how to read it so that you can see the relevance of standard deviation. Last session, I kind of briefly talked about standard deviation in this way. I said, in year 7, the only way to look at how wide a set of data is, or the spread, is what we're actually looking at, is you learnt range. And we said range is equal to maximum minus minimum. So what is the largest number minus the smallest number? So that was year 7, right? Then you get to year 8 and year 9. You get introduced to IQR, which stands for interquartile range. And in that session, which is our last session, you guys told me it's the 75th percentile, take away the 25th percentile, because it gives you the proper 50% of the data, right? So it's the middle of the lower end to the middle of the top end, so 25 to 75. Yeah, so I just said I forgot to print the notes. I wanted you to grab out your exercise book, grab out a pen or pencil, and just write the notes where I tell you to. So I haven't told you to copy this down. You don't need to. This is just me explaining. That's true. Jada, can you help me just turn off the light? Should be that one, yeah. Thank you. So you've done year 7 range, year 8, year 9, we do IQR, and then when you get to year 11, technically year 12, that's when we truly study it, standard deviations. If you do general maths, they do it earlier. So they do it in year 10 and 11, but they use a CAS calculator to calculate it. They don't actually study what it is. They just memorize it. Okay? Standard deviation is still a measure of spread, but it's better. So instead of the smallest number to the largest number, which is the width of your data, to the middle of your bottom end to the middle of the upper end, that's the 50% of the data, so 25 to 75. To now standard deviation breaks that into smaller quadrants or smaller pieces. And the standard deviation is usually a better measure of spread. And the reason for that is to do with this graph. That's why it links well. Okay, so what is standard deviation? It is a number that describes the would you say it's the distance of data about the, no, it's the, yeah, it is the difference of data about the mean. And I'll explain what I mean. I'll give you a logical explanation to it. And I kind of alluded to this idea in our last example. So what do I want you to copy? Write down standard deviation is a number that describes the difference or the spread. You can write over here spread if that makes more sense to you. It's the spread of the data about the mean. So we use the mean as the main popular, the area where most data will sit, because that's what the mean represents. And then from that mean, we're just looking at how far away from the mean is it. So the difference from the mean or the spread of the data away from the mean. So let's give you an example. I usually do this with my year 12. So I say, imagine I had a formula. Imagine I was this crazy genius mathematician, and I was able to calculate your ATA score, okay, just from simply knowing how many hours you study in a week. So if I asked you how many hours you study in a week, I will have a formula to give me a prediction. This red line that you're seeing is my formula. Okay, so that's the formula I've got. Let's say I picked 1, 2, 3, 4, 5, 6 students, and I asked them how many hours they studied. So say student A in scenario 1, student A is B, C, D, E, F. So if I ask student A how many hours you study, so let's say this is 2, wait, that's 1, actually, yeah, that's 2, 4, 6, 8. So the student A tells me they've studied 2 hours. I made a prediction that they would get 8 of 10. Okay, that's my prediction. Oh, actually, not 8 of 10. They were getting 20. So 20, 30, 40. Was my prediction good so far? or bad? Not terrible, but I was 10% off. Okay? So I said, I think if you study 2 hours, you're going to get 20. That particular student is 10% off from what I predicted, right? But if you take the same comparison, if I did it for 2 groups, this is another class that I teach. And I ask the same thing, student A, student B, student C, student D, student E, student F. Now this one I happen to get exactly correct. So the student who studied 8 hours got an ATAR of 50 and I was smack bang on. Which one out of these two, scenario 1 and scenario 2, was a better scenario in terms of my prediction? Would class 2 trust my prediction or would class 1 trust my prediction more? Which one? Class 1. Now, whatever you're doing in your head right now, because you're looking at the data, what you're doing is the standard deviation. You're able to tell that this is a pretty bad prediction for this scenario. Even though I got one smack bang on correctly, exactly correct, you can tell that I'm pretty far off with a lot of the other students. So group C, student C who told me 2 hours, I predicted they would get 20, but instead they got, 60 or 70. Yeah? And that consistently happened with each one. So we're looking at that now. How did you know that this group was better? You were actually, this is your mean. This is what I expect. It's what I predict in the long run, what students should get. This is the real data of what students actually get after studying. And this is their ATAR score that they get. Okay? And what you can see is, overall, my data, even though I'm not 100% right, which is really hard to be 100% right, I'm not too far off each time. Even though technically 10% is quite a bit. But that error difference, how do I work out the error difference? So this student here, he got an ATAR of 10, but I predicted 20. That's a 10% difference. The student here who got 50, but I predicted they would get 40. That's a 10% difference again. How am I calculating 10% difference? What's the formula if we had to come up with a formula to find the standard deviation? Vibes. Vibes. What do we do?
The actual result minus the what your prediction was.
Beautiful. Cannot be described any better. It is your actual data. That's what they actually write in the formula. It's the actual data. So actual X represents actual data minus, and I'm going to use this symbol here that's called mu, but that means my prediction. That means prediction. If I minus those two, that gives me a distance, how far off I am. But technically, the proper name for it is called error. That's how bad my error is. Okay? But you see, my error changes each time. I could be 1 off, I could be 10 off, I could be 3 off. If I want to know how bad I am overall, you would find the average error. Does that make sense? Find the average error. See how, on average, how bad is my error? Is it 10 generally on average, or am I only 2 error off, 2% off on average? So if you add them all together, so in this case, I got 1, 2, 3, 4, 5, 6 students. You would say sum all of my error divided by the number of error data or number of students I have. Does that make sense so far? Very good. So X minus prediction for every single one. So this one, find an error for that, find the error for that, find the error for this one, add them all together, add all the errors together and divide by the number of students I have. That should give me the average error. True? So this gives me, I'm going to do it on the side, average error. Now there's still a problem with this concept, because why didn't we just stick with that? That's a good formula, but if you look at the formula on this sheet, notice I've got most of them. I've got the xi minus mu, I've got the sum, and I've got n. But why is there a square root and why is there a square? So let's explain it. Here's a problem. What if I told you with the same scenario, this student was 10% off, this student was 10% up. So I predicted they get 50, but they get 60. This one I predicted they would get 20, but they got 10, right? 10% off. Now let's say I only got 2 students in this class. What's my average error? Should be 10%, right? But if we actually do the maths here, actual score, so let's say their actual score for this student was they got 50. I predicted they would get 40. This student, they got 10, but I predicted they would get 20. 10 minus 20 is negative 10. 50 minus 40 is positive 10. If I find the average error, what am I going to get? 0. So there's a problem here because I don't always have to be above the prediction. I can be below the prediction, but it's equally as wrong. Whether I predicted 10% more for you or 10% less, I am still 10% off. But the negative sign matters. So that negative sign, if I found the average of this, the average error, negative 10 plus 10 divided by 2 students, my average error is 0. But what does an average error of 0 mean? That I am perfectly, like I can predict everything. I'm on spot, which doesn't make sense. Oh, yeah, I know. So, because this is a problem, if we don't account for the signs, because I could be negative 10 down and negative 10 up, and overall I could be 0, the net result is 0, we have to counteract that. So the only way to deal with the negative sign, because 10 and negative 10 are different on a number line, but how do I make them the same? This is where squaring comes in. See, if I squared my error, negative 10 squared, what does that give you? 100. But 10 squared also gives me 100. So at least those two are the same numbers now. That's great. But what's the problem now? Because if we find the average error there now, 100 plus 100 is 200. 200 divided by 2, I'm now 50 error. What's the problem with that? That's implying that I have a 50% error on average. What's the problem there? It's wrong. You're now penalizing me so badly just because I was 10% off. You're now telling me I'm 50% off when I wasn't. I was only 10% off. Either way. Yes?
Isn't it meant to be 100 plus 100 200 divided by 2?
Oh, sorry. Yes, you're right. 200. Oh, sorry, 100. So that's even worse. I'm 100% error off. Right? So in the mathematics, I'm just so bad, right? So the squaring is a problem. So I squared it to counteract the fact that I had the negative. But then because I squared everything, everything gets inflated by squaring it. This is why the formula, if you look at the very first one, see that symbol? That's sigma. Why do we square root the answer? Because the square root of 100 will give me the correct distance that I was off. See, I was meant to be 10% off on average. That's why we square root. And that's why the formula that you see on your notes, which I'm going to go back. Where's your notes again? Right here. On your notes, can you see why they say this is your actual data minus what I predict for you to get. That's what mean represents, or mu represents what we expect you to get. Divided by the number of data. And this formula here is just the sum of numbers divided by number of numbers. So that's the average error. But why is it the error squared? Is because when we're calculating, there's positives and negatives in that zone. We square root it because we squared everything. So then you got to square root it back. If you didn't understand what I just described, that's normally at a year 12 level. I try to get them to understand what the formula is really doing. If you don't get that, you don't really need to. That's at the methods level where you're truly trying to unpack what it's actually saying. At the end of the day, this is just the measure of average error. Does that make sense? Okay, that just gives me an overall of the spread. How far off am I from the mean? So remember the definition I told you to find? It was the spread or the difference of the data around the mean. Yeah, so wherever the mean is, how far off am I from your expectation? And you did that intuitively. Before I even explained the actual mathematics to it, you all were able to look at this and say, scenario 2 is really bad. Scenario 2 wouldn't trust me with my prediction. Scenario 1 may more likely trust me. You did something intuitively. I've just spelt it all out mathematically. Does that make sense? Okay, so that's what standard deviation is. So the number for standard deviation, ideally the smaller the better. The smaller your standard deviation, which means error, that is a better prediction for whatever it is you're trying to do. Okay? All right. So that unpacks this formula here. This is your sigma. That's a sigma. It's the population, or technically we call it population standard deviation. These are just technical names. N is the size of the population. Each value from the when we say population, it's the group that we're testing. So in my case, it was the class, number of students in the class. And X is the value from the population for each student's actual score. And then the X bar on your calculator, that usually means the mean or expected average / prediction. We use mu to represent that. Do you need to know how to do this by hand? No. This is usually just me explaining it theoretically so that you understand what it means. Okay? So expected average or prediction or mu. Yep. Sure. You will just use a calculator to find these, which I'll show you how to. Okay? So I had 2 goals for you today. One is to understand standard deviation, so I explained it theoretically for you. How do you find standard deviation? It's literally what you did last session. Last session with the 5 numbery stats, that would have gave you the standard deviation already. I just didn't tell you which one it was. Okay? And that's why I'm going to practice the next page. And then you guys can practice your CAS just to practice getting it. Okay? Do you need to know these? No, not specifically. Okay, because you're going to do it on your CAS anyway, so you won't need to know these, but I'm just breaking it down for those who are. Yep, we'll do. Yep. All right, have we copied what we need to? Good. All right. On to the next page. Remember, I'll print these out for you to have hard copy for next lesson as well. But copy this, the numbers down that you're going to type onto your CAS calculator. So I want you to enter 2, 4, 5, 8, and 9. Like last session, you are going to go to your CAS and type the data in the spreadsheet. So number 1, open spreadsheet on your CAS. Enter the numbers 2, 4, 5, 8, 9 in column A. Call column A data. Call it data. Okay, so I'm going to go to my CAS. We're going to do it too. I'm going to start off new. So going to the new page, go new. Whoops. And I'm going to add list and spreadsheet. For those who forgot, from the home page, you can click on this. Click on that, and that will get you the spreadsheet. All right, column A, I'm going to call this data. Press enter, so it's column A is called data now. I got 2, 4, 5, 8, and something, and 9. So 2, 4, 5, 8, 9. Okay, so I got a set of data. Step number 2, you're going to click on any cell. Doesn't matter where. You can click on cell B1, for example. Then you're going to click on menu, statistics, stat calculations, 1 variable stats. Very much the same the way I did in the last session. So I'm going to do it on screen for you to see now. So here we go. Click anywhere. You can click on this cell if you want. Doesn't really matter. So I clicked on B1. I go to menu, statistics, stat calculations, 1 variable statistics, because I'm only doing 1 column. It's only 1 set of data I'm doing. Okay. So 1 variable stats. Here we go. Number of lists. There's only 1. Press OK. Where am I getting my data from? I'm getting it from the column called data. So change that to data. Everything else is OK. Just click enter or press OK. And then we'll have a look at, actually I'll change the mode just because mine's in exact values. Yours might look funny, so let's go change that to approximate. Now it's all in decimals. There we go. Let me know once you're there. So how did I go through this again? I just clicked on B1. I went to menu, statistics, stat calculations, one variable statistics. Press OK, OK. Just make sure to choose the set of data from column A, which is data. And then you would have got this. Once you get this tab, can I get a show of hands who've got this table so far? Or at least that entry? Okay, so far so good, good. All right. Yeah. If you've got an exact form, go to documents, so doc. Number 7 for settings and status. Then document settings, which is number 2. If you scroll down, it says calculation mode. For methods, we work in exact by default because it's always easier to convert exact to decimals. For general students, they use approximate, and then every other students might do auto. Okay, but for your scenario, I'm just putting in approximate so that you can interpret what the information means. So if you change that to approximate, press enter, and it will change it all to decimals rather than fractions. Okay. All right, so let's read what we've got so far. This here means the mean, so I know the mean is 5.6. This means the sum of numbers. Notice what this is. This is sum of squared numbers, but the one that we want is the sum of the x actual data minus the mean data squared. So this here is your standard deviation. One is the standard deviation for the population. One's the standard deviation for the sample. But you don't need to know that. You just need to know this number, 2.57. Okay, so it's that symbol. That symbol sigma, that's the one that you're generally looking for. So if they're asking for standard deviation, that's the one you're looking for now. Later on, you'll know the difference between the two. So general students will learn the difference between the two. Methods, not necessarily. And the 5-number summary, so you got minimum, Q1, Q2, Q3, Q4. And this is the sum if you wanted to do it by hand, but you didn't want to do the full calculations. This is the one that you do on the numerator before you divide by n. So remember that formula that I gave to you over here? That number was this one. That I'm highlighting, that's what that is. Okay, so that formula there, sum of your actual data minus your prediction squared, that's what that is. 33.2 is your, so if you take it out and work it out, this is meant to be square root. So let me do that again. Square root 33.2 is this number. That's 33.2. Divided by n, what's my data, number of data? I had 2, 4, 5, 8, and 9, so that's 5 pieces of data. So if I actually type that in a calculator, let's do it. So here we go, out on a calculator. I'm going to do 33.2 divided by 5. Gives me this, and then I square root that answer. That's where the standard deviation comes from. So 2.57, whoops, I'll go back to this one. 2.57, that number there, that's how they calculate it. Okay, so if you want to break it into pieces, we know now the sum of the residual square, that's technically what it is, but I'm not going to use that language, it sounds really complicated. It's just your actual data minus your predicted data squared, sum of all that, that's my average error. So average error is 33.2, and that's what I just did there. So I just showed you average error is 33.2. Divide by number of data. I have 5 data. 2, 4, 5, 8, and 9. Square root that. That's how you get your standard deviation. Okay, so I'm showing you if you were to do it by hand, that's how it would look like. This is what the CAS will spit out. So you just need to know this one, 2.57. Okay, if you want to break it even further, to do it actually by hand, the mean was 5.6. If you want to do it by hand, how did they get 33.2? 33.2 is the result of you doing 2 minus 5.6 squared plus 4 take away 5.6 squared plus 5 take away 5.6 squared plus 8 take away 5.6 squared plus 9 take away 5.6 squared. You see that? That's what this symbol means. So take your actual data. So I got actual data is 2, 4, 5, 8, and 9. What was the mean? We found the mean before was 5.6. So you literally do that for every one of them, sum them all together. That's how you get 33.2. Okay, so we go back, see the mean. The mean is 5.6. Your actual data was over here, 2, 4, 5, 8, 9. So you literally go through the formula and you would say 2 take away 5.6 squared plus 4 take away 5.6 squared plus 5 take away 5.6. And you just do that. That's how they got 33.2. Cool? What do you need to know? Remember, you don't need to do this by hand. I'm just showing you. I'm just showing you, breaking it all apart. So if you really wanted to know where it all comes from, you just need to get that 2.57, which you did from last session already. Okay? But I'm just showing you how to get there. Cool? All right. Can I get a show of hands who was able to find the standard deviation of that data that I just gave to you? So 2, 4, 5, 8, 9. You should have got a standard deviation of 2.57, roughly. Can I get a show of hands who were able to do that? Okay, because that's the skill I want you to take away. Okay, the theory I explain, but how much of it you get doesn't really matter. We're not assessing that. Yeah? All right, so again, I'll print this out, or you can look on OneNote. There's a digital explanation for it to go through each one, but I break it apart here for you to see. Oh, sorry, that's the sample one. Sample standard deviation. There should be one just underneath it, and that was 2.57. That's the standard deviation that you want. The one with the symbol. Okay. This one's something else. That's the sample standard deviation. It's still standard deviation, but we're talking about a sample, not a population. All right. So far, so good. All right. I'm going to give you about 2 to 3 minutes. I'm just going to pause the video. All right, this massive formula that you're seeing on your booklet, f of x is equal to 1 over sigma times root of 2 pi exponential, which is e, Euler's number, e to the power of negative half times x minus mean divided by standard deviation squared. That formula, you do not need to memorize. Okay, even the year 12s don't need to. If we do get them to use it, we give them the function. Okay? In a nutshell, someone has figured out this function. Okay, so what they realized is when you collect data in the general world, there is usually a group of data that sits in a certain section. Then there's small sets of data that starts to occur. They realize that the data set tends to look like what they call a bell curve. Mathematicians have actually figured out the formula for that perfect bell curve. And when I say perfect bell curve, this particular curve is special because the center is actually at 0 and the width is exactly 1 on either side. And what's special about it, so you notice within the formula there are 2 letters that are used here. You got mu, which actually means the mean. So that's the average. So if you know the average of a certain data, that's what that is. This represents standard deviation, which is the spread. And it turns out that in this special formula that they've come up with, when you type that in, this will give you a mean of 0 and a standard deviation of 1. Standard deviation is really hard to get generally. But to get exactly 1, this curve is not only symmetrical, but it has these 2 key properties. Now that's very special when you get to year 11 methods The reason why is because if you can start at 0, that means you can start anywhere else you want. See, the mean, for example, IQ. Does anyone know what the mean IQ is? Good. 100. Anyone know the standard deviation? Meaning, what's the next bracket? So if it's like 100 to get to the next bracket. 15. Very good. It's 115. So, generally, in a real set of data, on average, the population will have an average of 100 IQ. The next bracket up is 15 units away, and the next bracket down is 15 units below. What they found, or with this calculation and using calculus and all that, the probability of that occurring, which actually represents the area, that probability of picking someone that has an IQ of 85 to 115 is roughly 68% of the data. And that's the definition is one standard deviation to the left, one standard deviation to the right. So this is what they say. One standard deviation to the left and right of the mean, so plus or minus from the mean, is approximately 68% of the data. If you go to 2 standard deviations left and right of the mean, it's approximately 95. So that actually covers more people. So if I went another 15 on either side, if you're now getting an IQ of 115, 130, and then another 15 down, that's like 70 there. No, not 70. Yeah, it is 70. Where's 70? Yeah, 70. 70. This is now 95% of your data. Okay? And then the last one, 3 standard deviations to the left and right of the mean will give you approximately 99.7%. This is just a fact that you're going to need to know for our exam. Okay, so at year 10 level, this is all you need to memorize. At year 11 level, I will show you, or normally I show you where those numbers came from. Okay, and it's all coming from this graph and calculus to be able to figure out the area under the curve. But those facts there, 68, 95, 99.7 is what we're learning today. Okay, yep. Okay. So when you have a bell curve, you can measure the spread, meaning how far is it away from the mean. Now, the mean is where most people sit. So most people have an IQ of 100. When you calculate, well, they calculate the standard deviation through the method we just did before, they found that the standard deviation for IQ is 15. And what that means is that every width of 15 that you move to the right of the standard deviation, so if I move 100 plus 15, that gives me 115 now, or 100, which is the mean, minus 15 gives me 85. So now that's one standard deviation because I moved 1 to the left and 1 to the right. Then if I go 2 to the left and 2 to the right, that means 2 groups of 15. I'm essentially doing 100 take away 30. So 100 take away 30, take another 15 here, brings me to 70. And that's how I got plus 15. That gives me, and that's how I got 70 to 130. So this data here, if I go 2 standard deviations, so two widths apart from the mean, that will cover 95% of the population. And if you go to 3, it's 99.7. Yeah? And if you're wondering where that fact comes from, that fact comes from here. So this very basic graph is called a standard normal. This is when the mean is specifically at 0 and standard deviation is a perfect 1. And they've calculated that when you do 1 across, 1 left, 1 across, it actually covers 68% of the data. And that's what we use. So we calculate your ATAs. If you want to do a similar one, same thing, same idea as well. Anyone know the average study score for a subject? 30. 30 is the average, so they want 30 to be the average. Anyone know what the mean is? I mean, standard deviation. Just a bit less. 7. So, students who get 37 to about 23, 68% of you, or 68% of the population, we expect that they'll get somewhere for their study score for the 6 subjects they choose in year 12 between 23 and 37. And it's interesting because, you know, when students get 40 and above, a lot of students say, I want to get a 40 for my study score. But what they don't realize is how hard or how small of a percentage that is. And we can kind of roughly guess it as well. If this is 68% and it's symmetrical, right? What's the percentage from these two ends? We can calculate it. If this is 68, from 23 to 37 is 68. What's these two added together? 32, because it's symmetrical, right? So if this is 68, well, together it has to add up to 100, right? So that means there's 32. But if it's symmetrical, what's 32 shared equally? 16. So this is 16%. You got to be the top 16% of your subject in the state by the end of year to get a 37 and above. And if you actually calculate once, if you learn normal distribution, you can do it on your CAS. But from 40 onwards, it's actually the top 7.8% of the state, roughly. And if you go to 45, getting a rule 45 above, that's like the top 1%. So it's actually really hard to be the top 7.8 or say 8%. Because how many students do methods in a year? It's about 23,000. You take 7.8% of that, you're saying you are the top, whatever. What is that? Let's just guess that. Let's calculate that. 7.8 times 23,000. You're the top 1,794 of the 23,000 kids. In whatever subjects you're choosing, that's for methods, which is top 3 subjects in the state. English is even bigger. It's like 70,000 students. That's how hard it is to get a 40. That's why you go on the news. You can put your name on the newspapers if you wanted. You got a 40. So when students tell me and they say, I want a 40, do you know how many students say that? It's like at least 80% of the students will say to me they want a 40. But I know there's only 7.8% in general that will get 40 and above. It's actually a really hard feat to do. It's a lot of effort to do. Okay? Now, I just tangented off there, but hopefully you see the power of reading normal distributions. Okay? So what do you need to know for today? Copy this down. You should have. Now this is the proper way of writing it, but all I need you to have in your notes. Normal distribution. Draw a graph. Mean is 0, standard deviation is 1. Right? If that is true, there are 3 scenarios I want you to write down. Scenario 1, 2, and 3. If you take the mean plus minus 1 standard deviation, that will be approximately 68% of the data. Meaning, if I drew a picture and the mean was here, if you went 1 across, so mean minus 1 standard deviation and mean plus 1 standard deviation, that's 68% of the data. Okay, it's like saying mean is 100, 100 plus 15 is 115 to 85. That is 68% of the data. Versus if you did mu, mean, plus or minus 2 standard deviations, it's approximately 95% of the data. And then finally, the last scenario, if you add 3 standard deviations, it's approximately 99.7%. Meaning, if I drew the graph and this was the mean, and let's say we did standard deviations like this. So that's 1 standard deviation, 2 standard deviations, 3 standard deviations. Then this will cover approximately 99.7% of the data. Okay, that's all it means. So if you don't like the numbers and symbols I'm using, I can use the IQ example. So the IQ example, one standard deviation, so 85 to 115, that's 1 standard deviation. 70 is 2 standard deviations, 130 is 2, and then the next 15 down is 55 and 145. There we go. So 85 to 15. 115 is 68%. From 70 all the way to 130 is 95. And then from 55 all the way to 145, 99.7. If that helps you to understand. Okay, so that's all you need to know. Now, if you then look at the big graph that you have on your booklet, does this make more sense now? And you see why? -1 and 1, that's one standard deviation across. If you add 34 and 34, makes 68. If you go to the other side, 13.5 plus 34 plus 34 plus 13.5 should add up to 95. What's nice about that picture? It's because you don't have to do the calculations for each interval. They've done it for you. Okay, so all you have to do is just memorize those regions, or you can calculate it yourself as well. But that's all you needed to understand to be able to read. This is the center. If this is 34 and this is 34, that makes up 68 for the first standard deviation. If you're doing 2 standard deviations across, then we now know this is 13.5 extra, and that's 13.5 extra. So if you add just that section, it should be close to 45. Okay, because together it's 95. 95 divided by 2 is, sorry, not 45. 47.5. Okay? So you can see 13.5 plus 34 plus 34 plus 13.5 get you 95. That's what that represents. Does that make sense so far? Good? All right, let's do one problem, and that's it for today. And then you can then work on the booklet questions. Let's do a problem from the booklet. Let's do the first one. So on your booklet, can you flip over to the first example? Let's do that one together. So in your booklet, you've got your 68, 95, 99.7. Let's do the first question. Oh, it's an IQ one. Whoops. Oh, there we go. We've got a picture for it already. Here we go. 3, 2, 1. Let's draw this bell curve. Mean is 100. It says mean is 100. Standard deviation of 15. So we did it before. It was 85 to 115. 2 standard deviations now become 70 to 130. 3 standard deviations now become 55 to 145. Okay, so I'm drawing out the bell curve. Then we say, what percentage of people are expected to have an IQ of 100 to 115? So I'm saying from 100 to 115 is just this region here. That's only 1 standard deviation away from the mean. So what should this area be? Very good. So you expect approximately 34% of the data. That's all you're needing to know at a year 10 level in terms of normal distribution. We actually do calculations for that on the CAS with year 11 methods, which you might learn next year. But that's what we do. Yeah, so next one. What's the chances or percentage of choosing someone, or how many do I expect to get an IQ greater than 145? So I'm talking about this region now. So look at the front page. That should be able to give you a pretty good idea, or you can do your own calculations. Since this is 3 standard deviations, and this is also 3 standard deviations, we know this should add up to 99.7. So that means these 2 should add up to the remaining left over. What's left over? Yeah, 1 minus 99.7. Hey, what did I do wrong? Oh, 100. 100. 0.3, but then if you divide 0.3 equally for both sides, it makes sense. This is 0.15. 0.15 on either side. Okay, so can you see how I'm separating it? 3 standard deviations was 99.7. So the leftover is 0.3, but you have to divide in 2 to have it symmetrical. So that's why it makes sense. That's 0.15. But you could have also looked here, and that also tells you as well. So you can see after 3 standard deviations and above, it's 0.15%. But I'm showing you how I would calculate it if I didn't memorize this chart. If you don't memorize that chart, you can also calculate it logically. You just need to know 68, 95, 99.7. Okay? So now I know greater than 145 is about 0.15%. It's a very, very small number there. And then between 85 and 30, so we delete all of this again. 85 and 30, we're working between this point and this point. We know there's 34, 34, and 13.5. So you can say together it's 68 plus 13.5, 81.5% approximately. Okay, but again, you didn't have to do it if you didn't know the regions. You could have just used 68, work out that these sides is 32, and then you can minus what's left over for the 95 as well. You can get creative with it, but having the chart makes it easier. So if you're doing general maths in year 11, they will be given this chart. And if you're doing methods, we're not given the chart. We actually do the calculations on the CAS to find out the numbers. Okay, that's the difference between the two, but you just need to be able to read it at this point. Cool? All right, that's pretty much it. Actually, no, there's B and C here. Let's answer those questions. How many people are expected to have an IQ score between 70 and 85? This is different to before. What's different? They said how many people. So it doesn't make sense if you ask me how many people and then I told you a percentage. That's right. So I'm interested in the number of people now. So in this case, they told us there are 400 people. So you need to first work out the percentage. Then you find the percentage of the people. So between 70 and 85. 70 and 85 is this region here. That's 70 and 85. What's the percentage? Beautiful. That is 13.5%. Since we know there are 400 people in this IQ test or measure that this research is doing, it's 13.5% of 400 people. So that's 13.5 over 100 times 400, which really is just 4 times 13.5. I'm just going to write it out like this. And you get 54. So that tells you there are 54 people likely out of the 400 that I expect to have gotten between 75 and 85 for IQ score. Last question of your booklet that I'm doing for today. Between which two IQ scores would you expect to find 81.5% of people? Explain why this question has 2 possible answers. That's actually a good one. Maybe I'll leave this for next session for you to then answer. So next session is going to be your time. So on Friday, it's your time to digest this normal distribution stuff that I'm talking about. That's the only tricky part. Next week is pretty straightforward. Scatter plots and line of best fit. This is the only one that I thought was really theoretical. Okay, so I'm going to stop here. Have a think about C. Why is there 2 possible answers for 81.5%?